When running parallel multi-conductor armored cables, the equipment grounding conductor, or EGC, sizing becomes a critical consideration. Article 250.122F of the National Electrical Code, or NEC, addresses this specific scenario. The issue arises because the EGC within a standard stock cable may be undersized when paralleling conductors for current carrying capacity. This is distinct from paralleling conductors solely for voltage drop considerations. In situations where the standard EGC is insufficient, there is a practical alternative to ordering custom cables with upsized EGC. You can install multiple equipment grounding conductors in parallel to meet the requirements outlined in Article 250.122F. The key principle here is that the total ampacity of all the parallel EGC must be equal to or greater than the ampacity of the single EGC that would be required according to 250.122 or 250.122b. For example, if 250.122 or b calls for a 10 American wire gauge, or AUG, copper EGC with a certain ampacity, then the combined ampacity of the parallel EGC must meet or exceed that value. Crucially, all individual EGC that are connected in parallel must be of identical length. This ensures that the current is properly distributed among them. Let's delve into the specifics of how to implement this approach. Firstly, determine the required size of the EGC based on 250.122 or 250.122b. These sections of the code specify the minimum size of the EGC based on the rating of the overcurrent protective device protecting the circuit. Table 250.122 is frequently used to determine the EGC size based on the ampere rating of the overcurrent device. Secondly, select the size and number of parallel EGC such that their combined ampacity equals or exceeds the required ampacity calculated in step 1. For example, if you need an EGC with an ampacity of 30 amps and the stock cable contains a 12 AWG EGC with an ampacity of only 20 amps, you could supplement it with another 12 AWG EGC run in parallel. The combined ampacity of the two 12 AWG conductors would then be 40 amps, exceeding the required 30 amps. It's important to note that the ampacity of conductors is typically based on NEC Table 310.16 and associated correction and adjustment factors depending on the specific installation conditions. Thirdly, ensure that all parallel EGC are of the same material, typically copper or aluminum. Fourthly, ensure that all parallel EGC are terminated in the same manner. This means using appropriate connectors and lugs listed for the purpose and ensuring proper torque is applied. Fifthly, remember the length requirement. Each of the parallel EGC must be precisely the same length to ensure proper current sharing. Any difference in length, even a small one, can lead to unequal current distribution and potentially overload one or more of the EGC. This is a key point that is often overlooked. To provide a more detailed example, consider a scenario where you are using 3 sets of parallel 3/0 AWG conductors protected by a 400 amp overcurrent protective device. According to Table 250.122, a 3 AWG copper EGC would be required. However, the armored cables you are using have only a 6 AWG EGC. To meet the code requirements, you need to supplement the existing 6 AWG EGC with additional EGC. You could, for instance, run 2 additional 6 AWG EGC in parallel with the existing one. This would provide a total cross-sectional area equivalent to or greater than a 3 AWG conductor. Alternatively, you could choose to run a single larger EGC in parallel with the existing one. In this case, you would need to select a conductor size that, when combined with the existing 6 AWG, provides an equivalent ampacity of a 3 AWG conductor. The specific size required would depend on the conductor material and insulation type. When making these calculations, be sure to consult the appropriate ampacity tables in the NEC and apply any necessary correction or adjustment factors for ambient temperature or the number of conductors in a raceway or cable. Also, be aware of the requirements for bonding jumpers. Bonding jumpers are used to connect metallic parts of the electrical system to the EGC to ensure a low impedance ground fault current path. These jumpers must also be sized in accordance with 250.122. In summary, when dealing with parallel multi-conductor armored cables, do not automatically assume that the EGC within the cable is adequately sized. Carefully evaluate the requirements of 250.122F and supplement the existing EGC with additional parallel EGC if necessary. Always ensure that the total ampacity of the parallel EGC meets or exceeds the minimum requirements, that all parallel EGC are of equal length, and that all terminations are properly made. By following these guidelines, you can ensure a safe and compliant installation. Consider this other situation. Suppose you have 4 parallel sets of 500 kc multi-conductors feeding a large motor. The overcurrent protection is set at 1200 amps. Looking at table 250.122, you would need a 1/0 AWG copper EGC. However, the cable assemblers only include a number 6 AWG EGC. Clearly, you'll need to supplement the grounding. One option would be to install multiple number 6 AWG conductors in parallel along with the existing number 6 AWG. Another option could be to install one single larger conductor in parallel with the existing one. To determine the size of this single conductor, you would need to calculate the difference in ampacity between the required 1/0 AWG and the existing number 6 AWG. Then select a conductor size that meets or exceeds this difference. Remember that all parallel EGC must be of the same material, be properly terminated, and be of equal length. Furthermore, be aware of any local amendments to the NEC that may affect EGC sizing requirements. Some jurisdictions may have stricter rules or specific interpretations of the code. It is always a good practice to consult with a qualified electrical inspector or engineer to ensure compliance with all applicable regulations. And be sure that the connections to the grounding bus bar or equipment grounding terminals are appropriately sized and rated for the available fault current. High fault currents can generate significant heat, and undersized connections can fail, compromising the effectiveness of the grounding system. Regular inspection and maintenance of the grounding system are also crucial. Check for loose connections, corrosion, and any other signs of damage or deterioration. Address any issues promptly to maintain the integrity of the grounding system. Grounding is a critical aspect of electrical safety. A properly designed and installed grounding system helps to protect people and equipment from electrical shock and fire hazards. Pay close attention to the details of EGC sizing and installation, especially when dealing with parallel conductors. By following the guidelines outlined in the NEC and employing best practices, you can ensure a safe and reliable electrical system. Remember to always energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment such as insulated gloves and safety glasses. And if you are not qualified to perform electrical work, hire a licensed electrician. Electrical safety is everyone's responsibility. It is always better to err on the side of caution and seek professional assistance when needed. Never take shortcuts or compromise on safety. The consequences of electrical accidents can be severe. So take the time to do it right and protect yourself and others from harm. Always consult the latest edition of the NEC and any applicable local codes or regulations. The electrical code is constantly evolving, and it is important to stay up to date on the latest requirements. Participate in continuing education courses and training programs to enhance your knowledge and skills. And don't hesitate to ask questions and seek clarification from experienced professionals. The electrical industry is complex and challenging, but it is also rewarding. By dedicating yourself to learning and continuous improvement, you can make a valuable contribution to the safety and reliability of electrical systems. Moreover, consider the implications of using different types of cable armor. Some armored cables have the armor itself listed as the equipment grounding conductor. In these cases, the suitability of the armor as an EGC needs to be carefully evaluated, especially when paralleling cables. The armor's cross-sectional area and conductivity must be sufficient to safely carry the available fault current. If the armor alone is not adequate, supplemental EGC must be installed. Furthermore, remember that the path to ground must be continuous and have low impedance. Any high impedance connections or breaks in the grounding path can impede the flow of fault current and increase the risk of electrical shock. For example, consider a situation where you are extending a circuit using parallel conductors. You carefully size the EGC and make all the necessary connections. However, you fail to properly bond the metal conduit or enclosures along the circuit path. This creates a high impedance path to ground, which can compromise the effectiveness of the grounding system. To avoid this problem, make sure that all metal parts of the electrical system are properly bonded together and connected to the EGC. Use appropriate bonding jumpers and connectors to ensure a low impedance connection. Also, be aware of the potential for galvanic corrosion. When dissimilar metals are in contact with each other in the presence of moisture, a galvanic reaction can occur, leading to corrosion and degradation of the metal. This can weaken the grounding connections and increase the resistance of the grounding path. To prevent galvanic corrosion, use compatible metals or install insulating barriers between dissimilar metals. Also, apply a corrosion-inhibiting compound to the connections. Regular inspection and maintenance can help to identify and address any corrosion problems before they become serious. Grounding is not a one-size-fits-all solution. The specific requirements for grounding can vary depending on the type of electrical system, the voltage level, and the application. It is important to understand the applicable codes and standards and to design and install a grounding system that is appropriate for the specific situation. If you are unsure about the grounding requirements, consult with a qualified electrical engineer or inspector. They can provide guidance and ensure that the grounding system meets all applicable requirements. Remember, a properly designed and installed grounding system is essential for electrical safety. Take the time to do it right and protect yourself and others from harm.